Maths is a subject which is very fascinating to learn, and due to some complexes in it, people usually think and take it aside and they find it difficult to learn. But mathematicians have tried to make it simpler and more easier for different types of people and for different concepts to be easier and made more simpler to get it through a wider audience. So, one such concept which is very famous in mathematics and is very easy and is a very shortcut way of finding out a lot of things is the Pascal's triangle. Blaise Pascal, a French mathematician, discovered this triangle, but he didn't invent it because early Babylonian and Roman cultures were also inspired by the thought of this triangle. They used Roman numbers or any other symbols to denote the numbers, but the first Pascal's triangle is named after him because it came after the discovery of algebra and of Arabic numerals, which we see as 1, 2, 3 and so on, which you might out familiar with. So before talking about binomial expansion in Blaise Pascal's triangle, I want to say you what is a sequence. Sequence is a series of numbers. A series of numbers or any other figures or any other, you can say, objects which have something common in its succeeding or preceding pair. For example, in mathematics, let's take the easiest sequence, which is 1, 2, 3. And it can go on. I am taking 3 numbers for the sake of simplicity. So 1 plus 2 is 2. 2 minus 1 is 1. 2 plus 1 is 3. And 3 minus 1 is 2. So they have a difference of 1. So they have something in common. So now let's see the sequence. Let's come back to the Pascal's triangle and let's see that does it create some sequence or ring any bells in our mind. So first we are going to take 3 looks at the triangle. First we are going to take a horizontal look, then a vertical look, and at last a diagonal look. So let's take a vertical look. The first thing which I got to see by seeing the vertical rows is the numbers. How are they arranged? Let's see. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. And I am seeing that the numbers or the sum of the numbers is increasing from top to bottom. The first thing I see, it's not inverted, it's a straight pyramid. So let's add the numbers and let's find out something. What do we get from here? 1, we get it as 1, sum is 1, which is equals to 2 to the power 0. And why am I writing 2 to the power 0? Let's see from the second step. Is equals to 2, which is equals to 2 to the power 1. It's equals to 4, which is equals to 2 to the power 2. It equals to 8, which is equals to 2 to the power 3. Then 16, then 32, 64, then 128, then 256, and at last 512, which is equals to 2 to the power 4, equals to 2 to the power 5, equals to 2 to the power 6, 2 to the power 7, equals to 2 to the power 8, equals to 2 to the power 9. I will read to 9 because I feel making it more complex will be a very easy way to make people understand, and I'm joking fantastically. So we could say that the sum of numbers in a row is equal to some power of 2. What power of 2? It's equal to the row number from counting to the top. 0, 1. Because 1 is the second last number in this row. We can take in any way. The second last number will come as 1. In the next row, the second last number is 2. then 3, then 4. It goes to 2 to the power 4, 2 to the power 5, 5, 2 to the power 6, 2 to 7, 2 to 8, 2 to 9. We have counted 512 to make it simply easier. So the first secret is unwind by seeing the rows. We could see more in the rows, like that rows are very arranged, and the number of elements in the first row is 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8, then 9, and then at last 10. It depends upon the row number. That's also very unique. So this is one of the major secrets which we unwind while seeing the row. The second and the most important secret of Pascal's triangle, which we see row wise, is related to this term, binomial expansion. So let's take two numbers which are A and B. From the first, let's see if A plus B, we are doing it for addition, can also subtraction, but it would change signs, so it is easier for you to understand, and that will make it less simpler and more simpler and less complex. So A and plus B to the power 0 is equals to 1. What is the coefficient of A or any term of A? We can write it as A to the power 0, B to the power 0. So what is the coefficient? The only coefficient of the only term, which is 1. So the coefficient is 1. Let's take A plus B to the power 1. So what do we get? A to the power 1 plus B to the power 1. And the coefficients are 1 and 1. So the coefficients are 1, B to the power 1. So what are the coefficients? 1. See the second row. You might think this is just arbitrary, I'm speaking so. So let's look back to the third row. And let's take A plus B to the power 2. What do we get? You might be knowing the formula. It's A square plus 2AB plus B square, which the coefficients of A square and B square are 1. The coefficients of A square and B square are 1, and the middle term is 2. So you might think this is the third coincidence for this, but people say that once it can be wrong, twice it can be wrong, but 3 times it's always correct. Okay, that's not how we deal with mathematics. We might see for one more, the next column, the next row. So A plus B to the power 3 is equals to, you might be knowing the formula, I feel and I know, is equals to A cube plus, let me write in the second row so it will be easy for you, is equals to A cube plus 3A square B plus 3B square A plus B cube. Let's add the coefficients as 1 to just see. So what are the digits? So what are the coefficients? It's 1, 3, 3 and 1, which is equal to 4. So this is how people determine the binomial expansion of bigger terms. Okay, let's write a general formula for finding out binomial expansion. The general formula for writing out binomial expansion could be written as A plus B to the power n is equals to, let's take the first term, and as I would like to say it, let's take a little bit of concepts of permutation and combination, which I might talk in a later video. So I could write NC, for making it easier, let's write A coefficients as alphas. So it would be alpha 1 A to the power n B to the power 0 plus alpha 2 A to the power n minus 1 B to the power 1, and so on. It will go till alpha n, a to the power 0, b to the power n. So you might be thinking how to fix these things. Let's take the case for the fourth row. So the fourth row, let's take a plus b to the power 4. So alpha 1, which will be the first term which I would be saying, the first term in the fourth row, because it will have 5 coefficients, because it will have 5 terms and 5 coefficients. So let's write the formula for that. So alpha 1 for n is equals to 4. For n equals to 4, alpha 1 is equal to the one of fourth row. Sorry, I made a mistake. It should be n plus 1. Because there are one extra coefficients in every row. So let's write for the fourth row. A plus to the power 4 is equals to a 1 into a to the power n and b to the power 0 is equals to 1. So it will be equal to a to the power 4 plus, let's see the second letter, 4 plus 4, a to the power 3, b to the power 1, a to the power 3b plus, let's see, 6. Next number is 6. 6 a square b square. I have increased a power of b and I have decreased a power of a, plus 4 b cube a plus b to the power. This is how it works in the theory and the concept of binomial expansion. You could see easily that we are easily able to find the expansion of any power of a binomial by using this triangle. You might think this might be very difficult and we are not be able to for huge numbers. For huge numbers, we use permutation and combinations. So that might I tell you in later video. Let's go further about talking about this triangle. So this is the view when we were seeing the triangle row-wise. Let's see the triangle diagonally. The first diagonal, I'm saying this one, is just 1, which is any number to the power 0. Let's see the second diagonal. These diagonals create the natural numbers or counting numbers. How we count 1, 2, 3, 4, 5, 6, 7, 8, 9. The third diagonal is very, very intriguing. These are triangle numbers. These are the numbers from which you can make a triangle. For example, 1, which is the first number. So let's take a 1. Let's take then 3. Let's then take 6. So if we join the dots, we can make a triangle. Let's take 10. So you can easily say these numbers are forming a triangle because 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. So 1 plus 2 is equals to 3. 3 plus 4. So 3 plus 3. Now I'm adding one more number. Is equals to 6. 6 plus 4 equals to 10 and so on. So this is how I get the triangle numbers. These numbers can form triangles. Let's see the fourth row. The fourth row. The fourth row have tetrahedral numbers or the numbers which can form a prism. Let's see. Triangular prisms. 4. I'll make a triangle at the base and one in the top. It's a triangle prism. Let's take 10. I'm going to add one more triangle. I have to add 6 more. 6 more and I can make a prism. And let me show you how. prism numbers. It will look like a prism. Make a prism. Make a prism. Anyway, this is a triangle prism which I am making. Prism. Make a prism. Now let's take, because it's a 3D figure and it is saying about the 4th row. The second row said about 2D figures. The 5th row will say about 4D figures, but we can't really explain that as we cannot imagine 4-dimensional space. Our eyes perceive 3-dimensional space, we see 3-dimensional space, we live in 3-dimensional space. 4-dimensional space is beyond understanding, but it is predicted that if it ever exists, these modern and these stable figures will exist in the dot structures of 5, 15, 35, 70, 126 and so on, and so for 5, 6, 7 and other stages, but which might or may not be true. So now let's see a very haphazard triangle for the Pascal's triangle. I am going to make, I think you all have heard about the Fibonacci sequence. For this triangle, I will take, it's in a crisscross manner. Let's see. I'll take one, this, what is it? 1. Let's take another one. What is it? 1. Let's take the third one. What is it? 2. Let's take the 4th one. What is it? 3. Let's take the 5th one. What is it? 5. Let's take the next one. What is it? 8. So if we go on, we'll get 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and we can upgrade it wherever we want. Let's stop. It goes on forever. These are called the Fibonacci numbers. I've already made one video about these numbers, so I won't discuss much a lot, but I will just tell you that the third number in this kind of sequence, the third number is equal to the sum of the preceding two. So 2 is 1 plus 1, 3 is 1 plus 2, 5 is 2 plus 3, and these numbers form some special ratios which are related to understanding very important concepts of nature. These are one of the numbers which are very frequently used to define nature. So before ending the video, I would like to discuss to you a very important thing about the Pascal's triangle. Let's look at the vertical columns. 1, 2, 6, 20, 70. 1, 2, 6, 20, 70. What do these numbers imply? 1 into 2 is equals to 2. 2 into 3 equals to 6. 2, 3. Then 6 into, I can write 20 by 6, which would be 10 by 3, is equals to 20. So what I am going to see here? 2. Let's see just see the numbers. 2. 1 into 2 is equals to 1 into 2 is equals to 2. 1 into 2 is equals to 2. 2 into 3 is equals to 6. Now where the next sequence goes? So here comes 20. 20 is equals to 6 into 10 by 3. And so on. Let's see 70. 70 is equals to 20 into 35 by 10. So 20 into 7 by 2 is equals to 70. You are going to see the adjacent numbers. For example, let's take the next. Let's take first, I am asking 20 into 35 by 10. What is it? 20 into 35 by 10, or 7 by 2 is equals to 70. It will continue it forever. And it is very valid for other sequences also. So I would like to end my video about the Pascal's triangle, after saying this, that maths is very easy. We just need to know in what way we have to look at it. It can be very difficult for a very complex person who feels life is very difficult to understand mathematics. But there are certain ways in which we can make this subject a very inspiring and one of our best ways to study nature. Thank you.